In this video, we're computing the moment of inertia of a thick spherical shell that has mass m, inner radius a, and outer radius b. But this time, the density of the material is not constant. So we have a non-uniform density that we call rho, and that's dropping off like 1 over r. So up here, we're told that rho is equal to k over r, where k is just some constant, and r is the distance from the center of the sphere. Finally, as usual in our setup, we're asked to express our final answer for the moment of inertia in terms of the given dimensions of this shell. So we need to write that in terms of the total mass of the shell and the inner and outer radius. In other words, we need to eliminate the k from our final answer. And the basic strategy here is that we're going to use our previous result for the moment of inertia of a thin shell. That turned out to be 2/3 mr squared, and I'll post a link up at the top to where that was first derived. So before we get started, I want to do a quick review of some ideas about density. So the basic definition of density is that it's mass per unit volume, or m divided by v. That can always be turned around to say that a mass is a density times a volume. But when the density is changing, it's not this simple because the density doesn't have just one fixed value to multiply the volume by. So here's the basic idea of how we're going to split things up to deal with this. We're going to split this thick spherical shell into thin spherical shells of mass dm. Each one of those has a radius of little r and a wall thickness of dr. So to clarify, all the mass of that shell is contained within its thin wall. And because that entire thin wall lies at one specific value of r, the density is then well defined within that shell wall. So what we're going to do is take this formula, mass is density times volume, but write it in differential form. And that gives us dm is equal to rho dv. Now for a thin spherical shell, again, that density is well defined within the shell wall because the entire shell wall is sitting at one specific radius. So we proceed to write down an expression for dm. So again, our density at a distance of r from the center of the sphere is given by k divided by r. And then we do the usual thing for our volume increment. The volume of a thin spherical shell is given by surface area, that's 4 pi r squared, multiplied by dr, that's the wall thickness. Now one of these r's is going to cancel, and we find that the mass of our thin spherical shell is 4 pi k times r dr. So now that we have the mass of our thin spherical shell, we go back to our moment of inertia of a shell formula. So the moment of inertia of our shell is 2/3 mr squared, and we use that to build the moment of inertia increment, so the infinitesimal moment of inertia contribution given by our single thin spherical shell. So that's 2/3 times the mass, which is dm, times the radius squared. Now we just plug in our expression for dm. So combining the 4 out in front of that with the 2/3 out in front here, we end up with an 8/3 pi times k, and then the dm had a single r in it, and our di had an r squared in it. So I end up with an r cubed dr. Now that we have an expression for our moment of inertia increment entirely in terms of one variable, we just use an integral to sum those up. So the total moment of inertia is the sum of all the moment of inertia contributions. This is what an integral does. It adds up infinitely many infinitesimal contributions and tells you what the total is. So when we plug di into this integral, all the constants can come out in front. So I end up with an 8/3 pi k times the integral of r cubed dr. Now the limits of integration go from our smallest shell all the way to the biggest one. So that's a lower bound of r equals a and an upper bound of r equals b. Now the integral of r cubed is pretty simple. That's just 1/4 r to the 4th. And the 1/4 is going to cancel at 4 out of our numerator here. So I get a 2/3 pi k. And then we have r to the 4th evaluated from a to b. So we plug in the upper limit and we get b to the 4th. Plug in the lower limit and we get a to the 4th. So that's one way to write the final answer. But remember, we're trying to express the final answer in terms of the total mass and the dimensions of this shell. In other words, we need to eliminate k. Well, the standard trick for this is to do a mass integral over the entire object. In other words, I want to write down an integral that represents the total mass. That will come out in terms of k, and then we can solve for k in terms of the mass of this thick shell. So again, it's not as simple as saying the total mass is density times volume because the density is changing. Instead, to get the total mass, we have to sum up all the mass contributions of these shells. The farther out we go, the lower the density gets. And we already have an expression for dm. That was just 4 pi k r dr. So I'm going to move the constants out in front. That's 4 pi k. And then I'm going to sum all these up. And then I have an r dr. And we're summing up all these mass contributions all the way from the smallest value of r to the largest value of r. Again, that's just a to b. Well, r just integrates to 1/2 r squared. I'm going to go ahead and cancel a 2 as I'm working here. So now my constants are 2 pi k. And then I have r squared evaluated from a to b, which is b squared minus a squared. And this allows us to solve for k in terms of the mass. So the left-hand side of this equation, that was big M, and I just solved for k now. And that's big M over 2 pi b squared minus a squared. So now we go back and sub that into our formula for the total moment of inertia. I'm just going to replace k with m over 2 pi b squared minus a squared. All right, so a 2 cancels and a pi cancels, leaving us with a 1/3 m out in front. And then we have some algebra to do on this expression, b to the 4th minus a to the 4th divided by b squared minus a squared. And I'll just go ahead and do that work up here. So I have I equals 1/3 m, and then b to the 4th minus a to the 4th over b squared minus a squared. So we realize that b to the 4th minus a to the 4th is actually a difference of 2 squares. That's b squared squared minus a squared squared. So we can decompose this into a b squared plus a squared times b squared minus a squared, all divided by b squared minus a squared. And we get this really nice cancellation. The b squared minus a squareds are going to cancel out. And we can write our final moment of inertia as 1/3 m times the quantity. And then I'm going to go into alphabetical order here. A squared plus b squared. So the sum of the squares of the inner and outer radii for this thick shell. So that's our final answer for the total moment of inertia of a thick spherical shell with density dropping off like 1/r. In the next video, we're going to do one more example of a moment of inertia integral where density is not uniform. So the next one is going to be a solid cylinder with density growing quadratically from the distance to the symmetry axis. I'll post a link to that video at the upper left and a link to my moment of inertia integral playlist at the lower left, and I'll see you next time.